Thank you, Holly. Today's webinar will be brought to us today by Richard Weber. He is the Wetland Hydraulic Engineer on the National Wetlands team. Our topic today is Wetland Restoration Hydrology and Design Overview. We will have a couple spots where we'll take a pause for questions at about the midway point and then again at the end. So without any delay, let's go ahead and turn it over to Rich for the presentation.
Thanks, Bill, and thanks, Holly. And without further ado, let's go ahead and get started. Like a good presenter, I'm going to spend a little bit of time telling you what I'm going to tell you. And we're going to talk about wetland hydrology in terms of inputs and outputs, and put magnitude and vector and some time scale on those inputs and outputs. Now we're going to talk about the relationship between individual types of wetlands and a way to determine differences between wetlands and how that relates to those inputs and outputs. And we're going to talk about wetland types in terms of the hydrogeomorphic classification system. Many of you may have heard of HGM and rightly associate it with wetland functional assessment, but at its heart, HGM is a landscape classification system that works very well with hydrologists and engineers because it's largely abiotic. It ties directly to parameters of landscape, soil, and water. We're going to talk about different sources of hydrologic data so that we, at least in broad terms, know what kind of data we need to describe those inputs and outputs. And finally, we're going to talk about individual practices and planning alternatives and where certain practices are or are not appropriate based on those wetland classes. Key term is a wetland hydroperiod, and what hydroperiod is a term that describes the period of time in an average year that a site has wetland hydrology. Not all wetland landscapes are wet all the time. In fact, most aren't, and some wetland hydroperiods are very short, like that's indicated in the aerial photo with the playas in the Texas Panhandle. Those are a fairly short-term hydrograph, but that wetland wetland type has a very high level of function that depends on that hydroperiod being what it is. Well, it's like the one down in the lower right-hand corner in upstate New York. Those are wet virtually all year long. Sometimes the water on them is deeper than others, but in general, that surface of that wetland site is saturated nearly continuously. And in the lower left-hand corner, we've got a beautiful slide of a headwater close to the Continental Divide in Colorado, and we can still see a little remnant snow up on the tundra. So that snow melt hydrograph will basically, when it's gone, it will start ending the hydroperiod for that wetland type. Next key term, hydrologic regime. And we need to think of regime as a range. It's a range in depth, and that depth might be surface ponding, or it might be depth to groundwater, or the range might go from ponding depth down to a lower groundwater level. In the photo on the left-hand side, we've got three separate regimes in existence at this particular point in time in the hydroperiod in this wetland. We've got surface ponding. That ponding actual range might be from 12 to 18 inches, and it's probably closer to 12 inches. We have a surface saturated regime, and then in the foreground we have a wet meadow regime with groundwater at some distance below the surface. The point is that these three separate regimes respond to three separate functional types for wetland plant communities and the associated wildlife habitat. And finally, regime and hydroperiod go together in hydrologic terms to create hydrologic diversity. And hydrologic diversity means variation in those regimes and hydroperiods. In general rules, I just threw high points down at the bottom. Try to get deep water and shallow water. That's kind of the target for a highly functioning wetland system. So we have more than one regime in existence, at least after the capability of that landscape to maintain different regimes. which means certain parts of that site will have a longer hydroperiod than others. If we're doing a constructed project where we have the ability to physically move earth to modify the landscape, the flatter the slope, generally the higher the diversity. And the reason for that is very flat slopes create a large spatial extent change with a relatively small depth change. And as hydrologists, or those working with hydrologists, we need to be aware that there are tools available that allow us to make some really good decisions about matching calculated regime areas spatially with vegetative establishment techniques. The water budget is composed of parameters, and right now these parameters are just described in terms of quantities, but later I'm going to start putting vectors on those. But this is all the water budget parameters in general terms, except for tidal areas, which have tidal inflow and outflow. So all wetlands obviously receive direct precipitation. Evaporation, especially in our wetland context, is the loss of water off of a ponded water surface or a wet, bare soil surface, and transpiration is the loss of water through plant stems and leaves. We typically consider those together as ET, but it's important to recognize that evaporation off of open water or bare soil is not the same as plant transpiration, and especially in wetlands, that distinction can be important. Groundwater out of the wetland, that's G subscript O. Groundwater inflow into the wetland is G subscript I, and likewise for surface runoff, inflows and outflows. When we put algebraic signs on these vectors, we can compute a change in storage in the wetland, and this is basic water budgeting. Not all wetlands can be water budgeted, but many can. And it's also important to remember that storage is storage of ponded water on a wetland substrate as well as storage within that wetland soil profile. And in many wetlands, that soil moisture storage in the profile is as important or as large as that surface water. Okay, the Hydrogeomorphic Wetland Classification System puts all wetlands, basically all wetlands on Earth, into one of 7 separate broad HGM classes on the basis of these 3 parameters. Number 1, landscape position, and all that means is that certain wetland types with certain functions and surface water budget parameters only exist in certain landscapes and do not exist in others. All wetlands have a dominant water source, not the only water source. And again, obviously all wetlands receive direct precipitation, but in some wetlands the dominant water source is groundwater, which makes a wetland with drastically different functions than a wetland that has a surface water runoff dominant water source. And hydrodynamics is a term that describes a water budget vector in terms of direction, and those directions are described as horizontal or vertical, and water does move into verticals, into wetlands with the vertical vector with the groundwater discharge. So water does actually flow uphill in the ground. And those vectors may be unidirectional one way or bidirectional as water moves back and forth from a wetland to a source. The 7 broad HGM classes are riverine slope, the flats, which include mineral and organic soil flats, fringe wetlands along lake shores or the ocean coast, LACUSTRINE and estuarine, and finally depressional. And again, these are broad classes which really don't do us a lot of good by themselves. For instance, to describe a depressional wetland in South Carolina doesn't say anything about the fact that it's a Carolina Bay and not a high plains playa depression or a prairie pothole depression. So it's very important that HGM requires us to put some local distinctions on those wetland types. It'll make some good categorizations within a what we call a reference domain. But the broad HGM classes are these 7. So let's start with riverine wetlands very quickly. Obviously, they occur, like we might expect, on floodplains. And by floodplains, we mean active floodplains. Floodplains where the hydrology responds to the stream hydrograph. The dominant water source is the stream hydrograph, and so the wetland function and the nature of that stream hydrograph are intimately connected. And the hydrograph, depending on what kind of river system we're in, has a big effect on either surface water as flooding or, in a lot of cases, groundwater. And that's the instance in the slide shown here of a small, what we call macro topographic feature, which is an old abandoned remnant channel next to a fairly large river in eastern Wyoming. And we see water in this macro feature. We don't see any evidence of water flowing in or out of this macro feature. And that's because this is groundwater, and the level of groundwater at this point in time is directly connected to the level of the water surface profile in the river. And water in this feature will go up and down with the stream water surface profile. And the water moves in and out of this feature between the stream and the feature horizontally and bidirectionally into and out of. The key consideration for wetlands and riverine systems is a term called lateral connectivity. And when we restore wetlands in this landscape, if we do a good job of restoring the lateral connectivity of those surface and groundwater flows, then we've largely met our hydrology objectives. So this is what a stream hydrograph looks like. Hydroperiods are cyclic and repeatable, and we've got a good example of snowmelt hydrograph from the Tongue River, and again in Wyoming. And so in this instance, if we know that our wetland groundwater table approaches the surface at a flow rate of about 100 CFS, just in this particular instance, the width of the hydrograph that starting and ending at 100 CFS defines our wetland hydroperiod. And again, because of the snowmelt hydrograph, we have 2 successive years that show peak discharges around May going into June. It's also a good time to point out that if I'm fortunate enough to have good soil mapping in this wetland type or any wetland type, it's always a good idea to go to Web Soil Survey, take a few minutes, and print out the Soil Survey Water Features table. And it will give you 3 separate columns, and those columns will correspond to flood, frequency, and duration, and sometimes by month. It will also give you a column on ponding. Ponding is separate from flooding, and we're going to talk about that a little bit later, and also groundwater regimes. And so at least we'll have the first course interpretation of hydrology that's already incorporated into soil mapping. And of course, our primary source of data for riverine wetlands and hydrograph description is the stream gauge data, typically available through the U.S. Geological Survey or other sources. So this is what flooding looks like. This is dynamic flooding. This is surface flooding. The floodwater on this floodplain is there because we're at the high stage of the hydrograph. When the hydrograph goes down, the water is going to go back into the channel, and that flood inundation period will end. If we have any small surface depressions out in the floodplain, like we see over on the left-hand side of the screen and toward the top, those areas are capable of ponding, and that is a different regime, different dynamic. And in some cases where those areas are large enough, we'll have soil map units that actually have different interpretations. And so it's got a pretty direct relationship between what ought to be our planning objectives and the original features of the soil map. And finally, this is an episaturated condition. This water is water on the top, and in a case where our floodplain soils are not very capable of moving water through the soil profile laterally from the stream and the wetland, we really don't have a groundwater component to that stream hydrograph. It's all about the surface flooding, and that is episaturation in our riverine hydrology context. So shot up close, this is what ponding looks like after the hydrograph recedes, and we still have a fairly large area of ponding. Again, parked on the surface. The water's trying to move vertically downward in this situation, and this is episaturation. This is surface water. Taking a look at a restoration project, we see over on the right-hand side of the slide a straightened channel with a levee on both sides, and in the lower right-hand corner, hope you can see my arrow, we have the planners have decided to lower that levee to restore lateral connectivity for that dynamic floodwater to get into and out of the floodplain. And this is one of the primary functions of riverine wetlands is that dynamic flood, a whole host of reasons. So that restores the lateral connectivity of the flood hydrograph. In the interior of the wetland, the planners have elected to do some excavations of ponded surface water features. Again, what we call macro topography. And the flood hydrograph is receded long ago, but we still have large areas of residual ponding left over. Let's contrast this with another floodplain that's very different. In the foreground, we have standing vegetation, and we see some surface water evident. And if we look in the far distance, we can just see the water surface profile of the Tongue River, again in Wyoming. And the elevation of that water surface profile is not much different from the elevation of this groundwater surface. That's because this is an endosaturated floodplain. These soils are sandy and gravelly, capable of transmitting groundwater between the stream and those associated groundwater features and the macrotopographic features readily in indirect connection. And note that we don't really see any evidence of surface flow coming in or out of this feature in the foreground. And in fact, this floodplain does not require surface flooding at all to make it a wet floodplain. So this is a groundwater flood. Again, endosaturated. Taking a look at a large endosaturated floodplain, this is the Central Platte Valley in Nebraska, and that valley in most places still has evidence of remnant channel braids from back in the old days when the river really did get a large amount of snowmelt flooding from Wyoming and Colorado. If we go into a feature such as that and isolate it and remove material out of it to the point where we expose groundwater, we can express groundwater quite readily, again, in these endosaturated floodplain systems. There's a very important consideration in systems like this, especially when they get large scale. The valley slope in this part of the river is about 10 feet per mile. And so let's say, for instance, we excavate out a long channel braid a mile long. We have an upper end of that excavation that's 10 feet higher than the lower end, and it will tend to lower the groundwater at the upper end and convert that groundwater flow to surface flow and run it out the bottom end and essentially drain a large area of that valley, and again, for the purpose of actually restored wetland hydrology. And in no instance should we ever take those channel excavations and connect them, or those braid excavations, and connect them back with the active channel, because that surface runoff will be drained out of the valley and run directly back into the. So the technique that should be employed is to, if we're contemplating doing this type of excavation to expose groundwater, keep the length of those individual excavations short and separate them so that we have remnant material in between, and maintain them as individual, short, discrete ponded elevations, and we will maintain that groundwater elevation in affected sections of the valley. Going to get a little bit detailed here. Riverine hydrology can make use of a specific tool which we can reference in Engineering Field Handbook, Chapter 19, and it's called, in short terms, the Stream Inundation Tool. What that tool allows you to do is calculate a probability, duration, frequency flow, and what we're looking for is, well, for instance, the definition of farmed wetland, we know is 15 days of inundation on the average year, which we interpret to be a 50% chance 15-day continuous inundation during a growing season. This tool will give us inundation duration directly, so it's a direct solution for an episaturated floodplain. And if we're in the southeastern U.S. or areas in the upper Midwest and northern plains that gets a lot of long-term snowmelt hydrograph, a lot of our floodplains do have inundations of that duration. For those of us outside of those areas, we more than likely do not have wetland areas in our floodplains that will have water on the surface due to direct duration of inundation only. However, if we can establish a good relationship between stream stage and floodplain groundwater level, we can still use that probability frequency duration analysis to calculate the duration of our high groundwater, and there are methods to do that on a site-specific basis. And finally, to make everybody aware, the HEC Ecosystem Function Model, or HEC EFM software, has recently been CC approved, and it will take a long-term period of mean daily flow data as input, and it will accept any combination of probability, duration, or any period of the year you want to select as growing season. And furthermore, it will not only calculate exceedance flows, but it will also calculate average and minimum flows as well. It's a very good, easy tool to use, and the net result is the flow rate that corresponds to the flow rate that meets the input criteria. Moving up the watershed, out of Riverine, we're going to go to slope wetlands. The dominant water source of slope wetlands is groundwater, and this is where water actually moves into the wetland with a vertical upward vector. There's actually hydraulic head in a flow net starting in the adjacent uplands that collect precipitation and then into these wetlands. And they're typically found in low-order reaches in a watershed network, and in some parts of the country they're quite ubiquitous, and other parts of the country they're limited to small seeps and springs and headwaters. Where we have enough groundwater to discharge for a long enough period of time to start to form organic soil layers, these sites are typically called fins. And so fins, the takeaway point here is when you hear the term fin and used in the correct way, it should be associated with a groundwater discharge wetland. And again, when that groundwater discharge is long enough to maintain organic soils, which, by the way, organic soils do not exist without continuous surface, we might be in a fin landscape. So we've got a few shots here, upper right-hand corner, the Henry's Fork in southwest Wyoming. Lower right, we've got a small seep in Utah. Actually, this is a spring development site. And in the lower right, we have a wet meadow in the Nebraska Sandhills that is a groundwater discharge wetland that has been severely degraded by a gully moving up into the wetland, and this restoration with the sheet pile was meant to raise the groundwater surface back up and restore that groundwater level. Looking at the map of a watershed network, I apologize for the lack of brightness of the colors, but if we look closely in that dendritic watershed pattern, we can see in the upper reaches in yellow and orange and even light blue, these are low-order stream reaches that don't have enough flow accumulation and flow energy to form a channel floodplain system, and these are the reaches where we look for those headwater slope wetlands. The shape of the landform is concave across the valley and also concave longitudinally, and what the soil scientists call a concave landscape position in their geomorphic description. And it's this concavity that actually forces water topographically to the surface. Schematically, that's what these landscapes look like with the water budget vectors added in. The GI is groundwater discharge going into that wetland site. In this headwater reach, we got an RI vector because obviously we're going to get surface runoff off of the topography. And if the groundwater discharge is strong enough, we'll get a surface runoff discharge of the spring. The slope wetland boundary does not end when the spring flow emerges. The slope wetland boundary ends when we transition into a riverine reach where we have a landscape that's dominated by a true stream hydrograph. So here the dominant water source is groundwater, even though we get surface water runoff. In a riverine system, the dominant water source is a stream hydrograph, even though we might get a little bit of it. But slope wetlands are unique wetlands, largely unrecognized and, in my opinion, quite underappreciated, and because they have some unique functions that cannot be performed by most other wetlands. They serve to receive groundwater discharge and hold it for long-term release downstream that has a highly functioning capacity to maintain base flow in our larger stream reaches. And so really putting wetland restoration in a watershed context should focus on making sure that we do all we can to get these slope reaches and these headwaters back to the level of function. Because they can form organic soils, they have a strong potential function to sequester organic carbon. And when the hydrology is lost in these systems, that organic carbon that was previously formed will be exposed to oxidation, and all of that stored organic carbon in that soil will be lost to the atmosphere as carbon dioxide. Typically, critical upland water sources that don't exist elsewhere. One thing they don't do very well is provide areas of open water for waterfowl habitat, but they have a strong function of maintaining off-site benefits in the stream network for fisheries and other aquatic organisms. This is what a slope wetland looks like in, this one's Box Elder County, Utah, and we have an upstream shot of a slope wetland. We've got actually a water course here. This is spring flow flowing out of this wetland site, and we don't really have any landscape distinction between the channel and a floodplain. This is just all one single landscape position dominated by groundwater discharge. And downstream we have a gully advance moving up into that wetland. As the gully deepens, channel in sizes, the groundwater table goes with it, and that surface saturation in this out here the gully is now 6 feet or more below the surface. And we can see some remnant willows there, but they don't have much chance of regenerating because the site of this reach has been completely converted to upland. When we're looking at a reach like this, we need to be careful when we apply stream channel morphology principles, because these sites don't have a water course that corresponds with terms like geomorphic bankful discharge in quite the same way as we do when we actually stream reach with an active channel that's discrete from an active floodplain. The surface runoff hydrographs are short-term, but the groundwater discharge is long-term. In an extreme case, I'm going to direct you to look at the slide in the upper right-hand corner. This is a very large-scale slope wetland, surface saturated. We're at the peak of the hydro period in early spring. We've even got some nice hummocking, tussock sedge dominating the site. Really good, highly intact slope wetland, taking large amounts of groundwater and releasing it downstream to larger reaches in the stream network. If we misinterpret this landscape as one that should feature an active channel, we may make a decision to do something like we see in the lower left-hand corner, where we've constructed a stream channel, put some sinuosity in it, use all the techniques that we learn in channel morphology. But unfortunately, the net effect is going to be to lower the groundwater table from this channel, which is in effect a drainage ditch, and aerate the organic soil layer from the top of the bank down to the flow line of the channel, which over the next several decades will become aerated, oxidize, and completely cause subsidence in the land surface, and plus the loss of thousands of tons of organic material to the atmosphere. Slope wetland in the upper reaches of the watershed near the Continental Divide in Colorado. This is a especially interesting case because we've got a system that's maintained as a slope wetland by the actions of the North American beaver. And the beaver are maintaining a high groundwater table with a series of beaver ponds. We see spring flow flowing out of this system. The wetland boundary is clearly delineated here by the margin of the Engelmann spruce and the shrub willow. At some point in time, with enough sediment, the beavers will tire of building up those dams and maintaining ponds and move out of the system over the ridge into another reach. And at that point in time, likely we'll see a catastrophic failure of those dams and conversion of this site to something that might look a little bit more like a riverine reach. And this period of time will have the Engelmann spruce probably move down close to the channel until the next colony of beavers moves in and starts the system all over again. So in a case like this, we've actually got a temporal context to our landscape function. Discrete practice that's very appropriate for wet meadow-type slope wetlands or even small riverine systems where we think that the active channel does not maintain a water surface profile high enough to maintain that endosaturation in the adjacent meadow is to put in one or more rock check structures solely for the purpose of raising the water surface profile. And if we're doing this in the context of trying to improve the function of the active stream channel and a stream restoration technique, we ought to that the associated wetland functions are coming along with that restoration. This is an extreme case of a water surface profile modification practice in the Nebraska Sandhills, where a large deep channel has moved up through a wet meadow, and in this case, a sheet pile weir structure constructed in a cross vein orientation has raised the water surface about 3 feet and resulted in a pretty direct response of groundwater across a very large wet meadow. It's very important to approach this type of project with extreme care. In this case, this was the first of a series of structures in series, and this project will be stable as long as the downstream structure in series provides backwater to that structure during out-of-bank flows. And there are some very rational ways of doing that with channel hydrology analysis. Always remember, when we're raising the water surface profile significantly, we almost always need to consider putting structures in series so that they protect each other. And that last structure needs to be a point of confluence to a flatter reach downstream, or might even need to be a true grade stabilization structure. Mineral flats, another HGM class, and this is actually probably about the simplest one hydrologically. These are on broad, flat landscapes and uplands, and we've moved out of the watershed network into landscapes described as interflues. These are the top of ridges, and in places like Minnesota and northern Indiana, these ridges may be very flat and very wide. The mineral flat wetland hydrology only exists in areas of the country where we have an excess of precipitation during the wetland hydroperiod that's enough to actually maintain surface ponding across the landscape. Usually mineral flats consist of small discrete areas of shallow ephemeral depressions separated by other areas that are actually non-wetland. But the point is, the landscape is too flat for surface runoff to be directed into them, and it's too flat for ponded water to flow out, and it's essentially purged. Another key point to make, if we're familiar with the use of drainage equations, lateral effect equations, or modeling tools like DrainMod, the hydrology factors associated with this wetland type on this landscape fit perfectly with the assumptions of those lateral effect tools. And here's why. Hydrodynamically, we only have vertical vectors. Direct precipitation falling on the surface of the landscape, water in the soil profile, attempting to move downward through the soil profile into a deeper water table, and there are no horizontal vectors. No horizontal runoff going in, no horizontal groundwater inflow going in, and this matches up directly with the assumptions of classic drainage equations. If we have a landscape like this where we're doing a restoration plan, if we think we need to have a function that incorporates surface ponding or deep depressional areas in a landscape like this with no surface runoff water source, the net result will be to leave behind unsightly spoil piles and our excavated depressions with a few inches of rainfall in the bottom. This is not a depressional wetland landscape. And organic soil flats are very similar to mineral flats, except we're in areas where the net balance between precipitation and inputs and percolation and ET outputs is very high, and will actually build up organic soil on the surface just because of direct precipitation alone. And extremely common, but they do exist widely in the New England states. They also exist along the southern Atlantic coast as precosins. And they exist in central Florida, especially in large areas south of Lake Okeechobee. Rain-fed means ombotrophic, so that term is associated with rain-fed wetlands. And ombotrophic organic flat wetlands are commonly referred to as bogs. So we've got a distinction that I'll take the time to point out between fens and bogs. Fens are groundwater fed. The groundwater typically contains nutrients, so fens are typically nutrient rich. Bogs are rain fed only. Rain doesn't have any nutrients, and so bogs are typically nutrient poor, which is one reason why bogs typically are locations where we find some of our rare and endangered plant species, because those are species nutrient sources like pitcher plants or Venus flytraps that actually have to eat insects to survive because of the nutrient poorness. But again, these organic flats exist in areas where parts of the country where we have a high precipitation to ET balance. Estuary and fringe wetlands, these are wetlands that are simply dominated by the action of ocean tide. That might be the actual tidal fringe itself, or it might be as far up in a outlet stream that we're getting tidal influence. But tides are obviously very cyclic, twice daily. And one thing to point out with estuary and fringe wetlands is water typically moves in and out of these wetlands in discrete tidal inlet channels. Water rarely moves in and out as sheet flow. We actually have the channels that are in equilibrium with the volume of tide, which, by the way, is referred to as the tidal prism, and the flow energy and whatever sediment sources coming in. So the equilibrium in these tidal inlet channels is very similar to a stream channel equilibrium. And the tidal inlet channels also are very analogous to channels referred to as bayous in the lower Mississippi Valley, where water moves back and forth in the channel between the stream and the adjacent landscape. And Bill, do we have any questions we need to take now? Or? Okay, this is a good point to remind everybody that if you have questions for Rich, you can enter them into the notes bar at the right, and be sure to address it to all moderators. Rich, I've got a question for you. You've thrown out an awful lot of terminology so far: stream channel morphology, HGM classes, episaturation, endosaturation. If somebody wanted to get more information on what you've been talking about today, where would they go for that? If you go to the Wetland Team website, which I think now is under the Water tab of the national web page, and then go to Hydrology, there are a series of tech notes that cover riverine wetlands, wetland restoration planning scenarios, and especially a tech note called Soil Hydrodynamics for wetlands. And those, especially that tech note, has got all of those that terminology in it. All right. Well, that was all the questions I had at this point. We'll cover the rest of whatever questions come up at the end. Rich, why don't you go ahead and continue on? Okay. I'm going to forge ahead. Let's also talk about tidal inlet channels, and there are techniques for modeling the attenuation of tidal flows, either through a tidal inlet channel or through a tidal hydraulic structure. And this is a very common scenario along our ocean coastlines. And for those HEC-RAS gurus out there, if access a set of tide gauge data, typically hourly data, on a 30-day period of record, you can use that hydrograph as the downstream boundary condition for an unsteady flow model, and run it and see what kind of attenuation you get. The key point is the function of tidal. One of the functions of estuary and fringe wetlands is the attenuation of tidal flow, and also the attenuation of storm surge. And there are some techniques that haven't been employed a lot, but there are ways to do that. And if anybody's interested in that, contact myself or actually Carl Visser or John Fripp at the NDCSMC. LACUSTRINE fringe are similar to tidal fringe, except they occur on the shorelines of large lakes and it's important to remember that lakeshore itself is not a lacustrine fringe wetland, but a landscape formed by lake action is a lacustrine fringe. And that's pretty, I'm going to describe the slide over on the right-hand side where we have Yellowstone Lake in the background. And in the middle ground, we've got a dune. It was actually formed by lake wave action. And it's dry, obviously, because it's growing lodgepole pine. And then in the foreground, we've actually got our wetland, which is behind the dune wetland. And the water that we see present in that wetland moves up and down with lake level. And in some extreme cases, large lakes will set up lake seiches, which are basically long-term wind will raise the elevation along one certain shoreline of the lake, and those lake seiches themselves can raise the water level in those lacustrine wetlands. So the hydrology analysis of water movement in those wetlands can be done with lake gauge data, and actually even perform the same probability, duration, frequency analysis with that data as with stream gauge data. And finally, the default landscape position is depressional. These are out of the watershed network. They're not in floodplains. They're not in any other wetland landscape. And if closed topographic depressions form depressional wetlands. They exist all over the country in different forms. We see our Carolina Bay in the lower right, but playa wetlands that are depressional wetlands exist from the Texas Panhandle actually up into Wyoming and the western Dakotas. And then we have the prairie pothole region wetlands as well, all depressional. The dominant water source of depressional wetlands is maybe surface runoff, or it may be groundwater, or in some cases it may be both. But the point is, for a depressional wetland to have meaning in terms of wetland hydrology and hydrology tools, we have to have a relatively well-defined catchment area. In other words, depressional wetlands have an associated watershed, which we can analyze for surface runoff or even groundwater runoff calculations or groundwater discharge calculations. And again, I'm going to repeat, shallow ephemeral depressions in mineral flats have to be treated as mineral flats, and the reason is because we cannot define a surface watershed. And so, again, the lateral effects and drainage equations techniques that we use to analyze mineral flats are appropriate for those. They are not very appropriate for analyzing the change in hydrology of a true depression. We can separate depressional wetlands hydrologically as recharge or discharge. And a recharge depression is one where the dominant water source is surface runoff and the water in the ponded area is attempting to recharge a deeper underlying groundwater level. So this is a classic recharge wetland. Surface runoff and then groundwater GO moving out of the wetland to recharge the groundwater table. A discharge wetland is one where groundwater is discharging into the wetland. And so that's the primary distinction. And in technical terms, if the groundwater outflow is greater than the groundwater inflow, it's a recharge wetland. And the reverse is true for a discharge wetland. And in certain cases, if the groundwater essentially flows through a wetland, like occurs in quite a few wetlands in the prairie pothole region, it's referred to as a flow-through. But mainly remember recharge and discharge. And that distinction is profound enough that the actual evidence in soil survey and soil features can determine whether that site is a recharge or a discharge wetland. SPAW model, moving into a specific tool, SPAW model works relatively well for recharge depressions. And the reason is because SPAW model allows us to put a lot of detail in defining the surface runoff conditions of the contributing watershed. So the same principles that allow SPAW model to work very well for analysis of a pond or an ag waste storage structure also lets it work well, relatively well for recharge depressions. Again, groundwater is not much of an effect here, not much of a water source, and the groundwater loss in most of these cases isn't that high. One caveat, SPAW model tends to work better in more humid climates, and that's because of the complexity of the calculation of surface runoff with with daily rainfall data. So those in the arid west need to, I guess, be aware that the more challenging SPAW model is a more challenging tool to use in parts of the country. We can do a simplified water budget, again, in recharge depressions especially, on a monthly time step. If we have a good data source for monthly precipitation, and we can calculate monthly runoff, monthly evapotranspiration, and depercolation. And so basically this is a spreadsheet tool started from a hand calculation. And we go through September of 1 year through August of, or through September of that same year, basically the wetland hydroperiod as a checkbook type analysis. And this is classic wetland water budgeting. It's typical to find recharge depressions with agricultural landscapes, and in most cases that agricultural landscape has charged that wetland with an excess of sediment from soil erosion. And a common restoration technique is to remove that sediment to restore the original depth of the ponded depression. Perfectly rational approach. One thing to keep in mind in situations like this is that recharge wetlands typically, not always, but very typically have a shallow perching layer. If you're into soil profile descriptions, look for a BT horizon. That's a translocated horizon that often makes a perching layer. And if you excavate out that perching layer, you may drain out the entire wetland down to the recharged groundwater table underneath. Also, consider leaving the original A horizon, which might be buried by sediment intact, solely for the reason that A horizon has got an elevated organic matter content, which can perform or serve as an energy source or some important biogeochemical functions in the wetland. Data source for direct precipitation, especially on a monthly time step. For those of you, I think everybody in the country has the links working now, and actually anybody in the public, to go to ePhotog, select your county, go to Section 2, Climate Data, and then click on the Ag CIS tab, and assuming that county has active NOAA climate stations, you will get a WETS table. And WETS is not an acronym for anything, it's just the WETS table. And it will give you your average monthly rainfall as well as 30% chance wet and dry departures from average, as well as the wetland growing season. So this is the best direct source for monthly precipitation in a monthly water budgeting technique. Also want to talk a little bit about groundwater monitoring. Groundwater monitoring wells are a direct way to keep track of groundwater levels in wetlands, assuming we have enough time to collect that data. Hopefully at least through one wetland hydroperiod, and a monitoring well by itself will give us direct evidence of the free open groundwater surface. However, if we have the time and expertise to install a nested piezometer immediately adjacent to that open groundwater well, and put a slotted interval in that piezometer at depth, if we have groundwater inflow under vertical hydraulic gradient, we will see a water level in the piezometer higher than the water level in the groundwater well. And this is direct evidence of groundwater discharge. And in certain cases, we can come up with estimates of the actual rate of water movement using some soil hydrodynamic and saturated hydraulic conductivity calculations. But the qualitative knowledge of whether or not the water is discharging or not. Conversely, if the nested piezometer with a slotted interval at depth, if the water level in that piezometer is lower than the water level in the monitoring well, that means groundwater is moving downward. And so this nested well piezometer device can put direction on that groundwater vector. Moving into a typical stream restoration technique, I just want to point out that if we put in something like this rock cross vein structure, and it has the net effect of raising the stream water surface profile, we have, whether we intended to or not, increased the lateral connectivity between the stream and its adjacent floodplain. And if this is an endosaturated floodplain, we've also raised the adjacent floodplain groundwater level. So the techniques of fluvial geomorphology in this landscape are highly appropriate to wetland restoration. And again, the two slides I showed you earlier in a different context, but on a riverine or on a small water course on a slope wetland, techniques that tend to raise the water surface profile restore that lateral connectivity. Don't forget to consider installing these structures in series again, and also remember that the effect, depending on the wetland type, whether it's endo or episaturated, will be more focused on surface flooding or groundwater influences. Ditch plugs are a very common technique used in wetlands around the country, and they're appropriate everywhere where a ditch has been installed to drain that wetland, except ditches that are large enough to actually be a active stream channel. And then we need to think about some. But the net effect, again, is to reduce the groundwater outflow water budget vector, and also the surface water outflow water budget vector, and increase that wetland storage parameter. Sharp crested weir, talk about those a little bit. They're appropriate, like in this case, in a degraded slope wetland where we actually had a gully advance through the system and drain that, lower that groundwater table. They're a good alternative to ditch plugs in sandy soils where we have high permeability. They're also very effective in organic flats where it's hard to actually put fill material on an organic soil and expect it to stay. But if that organic layer is shallow enough, we can drive a sheet pile into a deeper substrate of usually sand in those landscapes. This is what a sheet pile weir looks like in cross section. All weirs need a appropriate bed key. They need an appropriate bank key, and they need a control section. And sheet pile weirs especially, most of the installation is below the surface, sort of analogous to an iceberg. So when you see a sheet pile engineer that's designed and installed properly, most of what's out there is below the surface. Don't forget that hydraulic structures are buoyant, and especially in a wetland landscape where our objective is to increase that saturated surface or saturated condition up to the surface. Buoyant forces are especially strong. The large picture on the right with that broken tube, that tube was submerged and flowing partially full at the time it failed. And because it was flowing partially full under inlet control, there was enough buoyancy to float it to the surface. The lower right is a typical agri-drain stop log structure, and those structures are subject to buoyant forces that is largely unrecognized. And the reason they don't fail any more than they do is because they typically are held in place by a drawdown tube and a principal spillway. That buoyant force is putting stress on those connections that we typically don't anticipate. Conversely, here we have a stop log structure out of precast concrete. Obviously, very little problem with buoyancy, but they're heavy. And wetland soils are typically pre-consolidated, saturated, and so we also have settlement and consolidation of those foundations. And with that, Bill, I can take whatever questions we've got.
Thanks, Rich. We've got a few, and I'll give you a couple here. We've got a question. Could you go over the difference again between a depressional wetland and a mineral flat? They seem to be quite similar.
Okay, yeah. Honestly, it's nuanced, and I don't know where the questioner came from, but if they're from Minnesota, I can kind of sympathize with you, because we have a certain limited toolbox to analyze hydrology, and we can't apply the same tools across the board to both of them. But in general, if we have a depression that's, and I'm just going to say that has a depth up to 12 inches, and we've got a defined watershed where we know that water is flowing into that depressional wetland, we need to think about water budgeting SPAW model analysis type tools to analyze that. If that depression is really shallow and really broad and not very deep, and on a really flat landscape, so flat that we can't define a contributing watershed, the drainage equation tools that model groundwater drawdown are basically pretty appropriate for that, because we're really not drawing down deep depressional storage. And frankly, we don't have another method. And I hope that was a little clearer than mud. I know it's kind of problematic, and actually that's the subject of some discussions going on in the prairie potholes right now.
All right, I've got another one for you here. Can you please explain how to calculate groundwater recharge into some of these? You spent some time talking about groundwater-dominated wetlands. How would we account for that that recharge from those into those wetland types?
Yep.
Is there where would and maybe is there an equation or reference that you'd go to for that?
I struggle with that myself, and I'm going to answer that question in two separate components. If we know the direction of water movement of groundwater, in other words, if we actually know the groundwater is physically discharging under hydraulic head, we've got a qualitative assessment of the hydrology of the wetland. We don't have any quantitative assessment. Coming up with the actual volume of inflow is extremely difficult and requires probably more investigation than we can afford to do. And I'm sorry that's the answer, but that is. However, if we really wanted to quantify groundwater inflow and we had the head differential between the open standpipe piezometer and a groundwater well, and we knew the elevation difference between the slotted intervals, and we had a good idea of the saturated hydraulic conductivity, we could solve Darcy's equation for that. And if we had enough wells to characterize that across the wetland perimeter, we actually could quantify it. But the level of intensity is usually not worth it. And frankly, the qualitative knowledge of whether that water is actually discharging under head is enough. And by the way, any wetland that's got strong groundwater discharge is almost always almost nearly continuous groundwater discharge anyway. So we've almost always got excess water that flows out of the site as a spring flow.
But that quantity of groundwater can change over time through the seasons, too. That's one thing I would have mentioned is that over time, it's one thing to go in and measure groundwater inflow, but that groundwater inflow can change over time. So it's a pretty intense study that you'd have to do, involving nested piezometers, and it's not something, like you said, Rich, that we typically do.
No.
At this point, Holly wanted to interject something for us here real quick. Holly?
Yeah, thank you, Bill. And Rich, you've not necessarily seen the participation, but we've had really big numbers today. Close to 500 people have been in the webinar. And I know many of you are going to want to go back to conservationwebinars.net to complete step 2 to get your CEUs. And I just wanted to mention that as long as you have that web page open that offers you step, you don't have to click it right away. You could give it a few minutes, or you can try to jump in early, one way or the other. But if you leave that web page open, that link is still going to function for you in the next several minutes. So if everybody's trying to hit the site at the same time, we can slow that down just a bit. The other thing I was going to mention that Rich made mention of the web page for the wetland team, and I have put a link up to get people to that site at conservationwebinars.net for the web page that has the information for this particular webinar. And somebody also asked a question about whether or not there was going to be a replay available. And yes, the replay will be put back at conservationwebinars.net in about a week, the same page. So instead of joining for the live event, you actually view the replay. And those are my comments, and I'll turn it back over to you, Bill.
Thanks, Holly. We've got a couple more questions I'll go through here, Rich. Somebody was asking a question about if you could address this, Rich. Some farmers are adjusting their calcium levels in their soils to increase infiltration, and could this process be impacting wetlands due to that modification of permeability in sealing clays that are dominated by sodium?
I had heard that's fascinating. I guess if it's got the property to deflocculate the clay, yeah, it definitely could. Especially if you're in a episaturated ponded wetland type where that water's trying to move out through a substrate, and anything you can do to increase that KSAT will, reduce the hydroperiod.
Here's another one. Somebody asked if you could add a little bit more to this, with this question. Estuarine fringe in the Great Lakes coastal areas. You got siege effects, storm surge, wind surge, riverine flows that all contribute to estuarine hydrology. Aside from the obvious salinity differences between the Great Lakes and tidal, your coastal tidal, any other considerations for freshwater estuarine systems?
Probably a limitless number of considerations. What we can analyze with the toolbox we have is going to be based on the combination of lake gauge data, tide gauge data, stream gauge data, and whatever hydraulic structures or pathways we can model. And that's about the best we can do. That coupled with evidence we can gain either from an on-site soils investigation or soils mapping, hopefully will be enough to get us going down the right direction.
How about any freeze-thaw type of situations that we need to be aware of or thinking about, Rich? Freeze-thaw
is, I think of that more in terms of wetland structures and structure function. Ice effects on stop log structures or freeze-thaw effects on compaction of material in a saturated substrate. But in general, when we model wetlands like in the northern plains, we tend to be able to get away with modeling based in terms of rainfall and data for runoff and without having a whole lot of trouble with freeze-thaw cycles. That being said, if you get into really intense hydraulic modeling procedures for the appropriate landscape like drain mod, there are some parameters in there where you can allow for frozen ground and its effect on water infiltration into a soil profile. And I know that wasn't very clear.
Could you talk a minute, Rich, about the NEDS course on wetlands hydrology and wetlands restoration?
Sure. Yes. Good plug, Bill. Bill is on the Wetland Hydrology Tools category, along with myself and some other highly qualified hydrologists, and that course specifically addresses the use of hydrology tools. It's a hydrology-based course. It's been taken successfully by non-hydrologists very well, but all the techniques that are currently available for modeling wetland hydrology are covered in that. The Wetland Restoration and Enhancement course is a week-long course that I'm the category leader on that one, and we cover wetland science from soils to wetland plant communities to wetland hydrology to wetland habitat restoration techniques and that sort of thing. So it's a broad-based course on wetland science appropriate for all disciplines. And the Hydrology Tools course is a detailed course appropriate for those interested in actually doing wetland hydrology modeling.
So those are two NRCS employee courses. I got one more question for you here, Rich. what do you think, could depressional wetlands in the prairie pothole region be a source of recharge for the Ogallala? And I probably massacred that aquifer.
Yeah, the Ogallala aquifer, the true Ogallala aquifer, plays out at pretty much the southern South Dakota border, and the wetlands in the Nebraska sandhills. That's part of the aquifer, and those wetlands are basically fens. They're groundwater discharge wetlands. As you get out of that landscape into the Dakotas, if we have depressional wetlands up there, most of those, I think, are recharge depressions, and I don't think they have a significant connection with the Ogallala.
And in prairie potholes, a lot of those are pretty low hydraulic conductivity. There wouldn't be much getting through those. I mean, I guess if they were wet for long periods, you could. Yeah.
It's interesting. Those prairie potholes, they are evenly divided between recharge and discharge. And as a matter of fact, the soil scientists in South Dakota have got a pretty good handle on what soil map units correspond to, whether they're recharge wetlands that actually perch water and discharge wetlands where groundwater flows into them. And generally, the recharge wetlands, well, I'm just going to throw it out there, the Tonka and Tatonka soil series, those are classic recharge map units, and the Southam and Parnell series up there are discharge, and they know they're discharge because they have a calcic horizon and some other indications of a mineral-rich groundwater discharge that is left behind by that. And the recharge wetlands tend to be smaller and shallower.
We had a question somebody was asking about access to the NRCS employee courses by some of our partner agencies out there. And I'll just go ahead and answer that one. That access to the NRCS courses is on a space available kind of relationship. We've had some folks, outside NRCS folks, who have attended those in the past. And in fact, the Wetland Hydrology Tools course originally was a course that was Corps of Engineers, NRCS, and Fish and Wildlife Service all attended that course pretty regularly.
Yeah,
well, Rich, that's the last question that I'm seeing here. I want to say thank you for presenting the topic today, and your contact information is there on the last page for those who may have some questions that you'd like to talk to Rich personally about. I'd encourage you to do that.
Yep, feel free.
Any final words, Rich?
No, appreciated the opportunity. And, yeah, anybody that has any follow-up questions, feel free to drop me a note on my email address, and I'm looking forward to it.
All right. Thank you very much. That brings today's webinar to a close.